sort of context, what's the background goes here? So who has seen MVPs before? Oh my. Okay. Well, okay, then you okay. Who could go out right now and program value iteration? Okay, it's a little bit better. Okay. So the first half is a lot of background. I think a lot of you will find this very obvious if you've already seen MVPs. The second half is on state-of-the-art methods for planning, and that's by Bill and S. And so the second part I think you'll definitely enjoy. Should largely be new to you. Okay, so just on my background quickly, if you knew me 15 months ago, I was at NICTA in the ANU in Australia. I moved briefly to Oregon State for a year, lots of great MVP people there. I had a great opportunity to join industrial engineering at U of T, so I just moved there in April. So it's my current affiliation and hopefully my last affiliation. Okay, so the lecture goals. I find there's not enough emphasis on modeling problems in MVPs. I've seen tons of students who know value iteration and can program all the solution methods, and they have no clue how to formulate the problem. And that's really critical because the way you formulate the problem will affect the solution that you want to use. So I'm going to spend a lot of time on the formal ingredients and the different assumptions that you can make. Okay, then I want you to understand the very fundamental solutions. The simplest ones, not the ones you go out and implement tomorrow. They won't win competitions, but just the ones with the core properties that you should understand. I want to briefly digress on how to build complex models. So who's heard of PDDL at this point? Okay. Who's heard of RDDL or Riddle? Okay, we all know after today. So PDDL has some limitation for stochastic models, and I try to address that in another lecture on Riddle. I'll cover that. And finally, this last part is more content than what I'm showing here, but it is what Joel's going to cover. So basically, what's the state of the art? Joel will cover AlphaGo, cover some really, really great work on that he's also done on learning to play Atari just from video screens. Okay. So definition planning under uncertainty is a rough definition computing sequences of actions or policy to achieve periodic rewards in a known stochastic environment. And I want to differentiate that because, you know, if you work with MVPs, you often have heard of reinforcement learning. What's the difference, right? So still learning to act, but the key thing here is that the environment is unknown. So all you can do is sample. And you can optimize the policy by sampling, or you can try to learn a model in the samples and then plan the model. But reinforcement learning is inherently different from planning on uncertainty. I'm going to focus on planning on uncertainty. Joel, towards the end of this talk, will get a little bit into what happens when you don't have the model. No, actually, yeah. Yeah, the compression part. Okay. So before we discuss how to solve MVPs, let's first assert that they're actually useful for real problems. So look at elevator control. You wouldn't typically model this as a deterministic planning problem. Why? Because there are lots of, at least I would say this concurrency in action, that's fine. Deterministic planning can handle that. But the key thing is you have random lives on the floor. People going up, people going down. Where are they going? Right? These are stochastic. And you have to plan is the uncertainty of the future. The objective here. So one thing in MVPs, a lot of time in PDDL, you get goal-oriented planning or cost to goal. So in general MVPs, people typically work with very rich rewards, or cost to goal and beyond. So you have many different objectives. For example, minimize total wait time. Can someone give me a different objective? So there's one problem is summing over the wait times of all the users. Is there a better objective that's more fair? So I really interact to make sure people stay awake. And I won't go on to some piece up.
Minus expected wait time?
Sorry?
The expected wait time?
Yeah, so what is the sum, the cumulative expected? It should be a normalizer. Yeah. Right?
Maximum wait time?
Yeah, exactly, right. So you might want to minimize the maximum wait time. So you know, this one can make somebody wait 5 minutes because everyone else gets served in 5 seconds, right? It's good overall. I mean, it's good on average, but you kind of need an objective. You might want to minimize the worst case wait time. It depends. Okay. Finally, now this is, I usually say elevators cannot reverse direction people in them, right? There's constraints on the policies. And that actually was violated today in the elevator. I've never seen an elevator do this to me before, but reverse direction. Okay. So is this happening to you, camera? I was in the elevator. Okay, so two-player games. Joe will get into AlphaGo in that solution. That's the bottom game Go here. Here you have your action, your opponent's action. If your opponent's intelligent, then they're not just part of the environment, right? They will actually adversarially try to optimize. And that's sort of kind of a min and max in DD. I won't go too much in it, but the point is that now the response to you is not just stochastic, it's adversarial. So Othello, difficult game solved by regression and search. Backgammon solved many years ago by neural networks and limited search. And lo and behold, AlphaGo, recently world champion or beat a Go professional, and it's neural nets on steroids, right? Deep nets, but still search in this type of multi-touch research. Not surprising, the same ideas work over and over with modifications over the years. Okay, so multiplayer games. So these are two-player games, right? But you know, think of poker. And I love this. Like, you haven't played poker until you manage to be part of this game. Okay, so here you have strict uncertainty. I don't know what's in your hand, right? So this is an issue, right? How do I model the world when I have absolutely no knowledge at all, stochastically, of what's in your hand? So this is a case of strict uncertainty, very different from stochastic uncertainty. In strict uncertainty, you have a set of possibilities or intervals of continuous. You have multiple rounds, so sequential, right? Because there are sequential things you do now may reveal information to your opponent, they get more information, they can monitor state better. Okay. And it's partially observed, right? Because you don't see what the state of the opponent's hand is in poker. Okay. So Darpa Grand Challenge. Here's where you get to the extreme of the NDPs and POMDPs. And I wouldn't claim that someone's writing down an NDP or POMDP model, but I do want to make the claim that it is the underlying, POMDP is the right underlying model of these problems, no matter how you solve it, whether it's ad hoc or formal. So driving part is extremely complex, tons of observations to deal with, and a lot of real-time aspects. So many partially observable, where your sensors are very noisy. You see multiple sensors to help disambiguate what the state is. And for this part, you don't know the modeling environment, right? You have an idea what your actions will do, but you really have to wait and see what they do, have a more policy-based approach. Okay. So, is anyone in robotics? Yeah, so how about robots on carpet? Anyone ever have problems with robots on carpet?
On carpet?
Yeah.
On artificial grass, actually.
Artificial grass.
Robots working on artificial grass.
Okay. So I'm not a roboticist, but I've heard of carpet. Carpet has a grain, and so if you go in one direction straight, it's hard to drift to the right because of the grain. And it's really, like, we don't notice it, right? It's whiskered up roboticists. You don't always know your orientation and which way the grain is going. So you have to account for the fact that you don't know what the kind of reaction is going to be. Okay. So that's a lot of these problems, right? I mean, autonomous driving, huge, big deal now, poker, two-player games, elevators, something else stochastic, something else sequential, right? So how do we model all these different domains? The 6-tuple, that's all you need. Okay. Okay. So let's start thinking about that, how to model domains. So you've got one agent, say we're acting this agent in the middle, and they have this not so menacing robot over here. The agent has multiple actions, and I call this factored action state, right? You can move its arms independently of what its treads are doing. It has observations, right? The things that it does observe, but there could be other menacing robots in the background, right? Which are in the state, right? Which it doesn't observe. But it's always good to have some model what its possible state can be. So the one thing is, don't confuse observation with state, right? Very different things. The observations are stochastic and partial. state is the true state of the world, which you may or may not know, depending on whether it's MVP. MVP is fully observed, POM-VP is partially observed. Okay. So observations, what can they be? Distance from the car to the edge of the road, right? My opponent's bet in poker. Okay, so states, at any point in time, the system is in some state, right? So here for observation, the distance from the car to the edge of the road, my opponent's bet in poker. But now in the state, you actually know the actual distance, or the state will work in the actual distance to the road. And again, if partially observed, you work in a belief in that based on the observation. Or your opponent's count of cars in poker, right? That's in the state. Again, you may have beliefs in the state, but you don't have to directly. The actions can be concurrent, right? In this case, your actions are really across part of space of individual action spaces, AI. Okay, all actions need not be under the agent control. So, for example, in the game Othello and poker, right? The actions taken by the opponent, right, were quite adversarial, concurrent. And so it's interesting to note that there are two types of opponent models, and they lead to very different solutions. So you have a game like Othello and poker where I take an action, my opponent takes an action, and we go back and forth, right? And this can be solved by min-max search in a tree. You cannot solve problems with concurrent turns easily by min-max search. Think of highway driving or soccer. Why not? So what's the space? So here, deterministic policies, right? The best response to what my opponent would do will work. What's the best response here? Is it still a deterministic policy? Think of rock, paper, scissors, right? Should I just always choose rock? Probably not. Very predictable. So what's the optimal strategy in rock, paper, scissors? Gotta be awake. Anyone? Rock, paper, scissors, right? Yes, random, right? Okay. So the thing is, when you have concurrent actions with you and your opponent, right? You actually the optimal policies are in the space of stochastic policies for you and your opponent. So for example, this is sort of Nash equilibrium, right? So the one-third rock, paper, scissors policy is a Nash equilibrium, right? If any agent is taking that policy, no other agent would defect unilaterally from that policy, right? You can't beat that policy. So, okay. Finally, in terms of actions, there are exogenous, and there are things that aren't under your control, that aren't under an opponent's, not under an adversarial opponent's control, but there's still things which can be considered actions or events, right? So events due to nature. These are assumed to be stochastic. So the random arrival person waiting for an elevator, it's not that people come to the elevator and say, what's the best way to screw up the elevator policy? You know? No, they actually just want to get downstairs. And so in the morning, more people go down, in the evening, more people go up. Okay. So that's random events, random failure of equipment. And basically, if the exogenous events due to nature are uncontrolled, typically you don't necessarily model them as actions, you just model them as random variables. But it's important to realize that they are actions under nature control. Okay, so we have states, we have observations. How do we relate the two? Okay, so in your POM-VP, there's three cases, right? You have not observable. So your observation set is empty, right? So think of heaven versus hell, right? You know, we go through life. You know, we do what we think is the right thing. At least in my case, I don't have guys like Scott. You did well today. Tomorrow, Scott, you didn't do well, right? You just have to get to the end of life, and then you get feedback and you take heed, right? That's a non-observable problem. You act according to what you think is right. In the end, you figure out if you're in the right state. There actually is a POM-VP called Heaven and Hell, and the optimal policy is you see the priest first, and then this would be great, which goal state you should end up in. Okay, so you have the opposite in the spectrum. You have the fully observable case, right? which is the case we're going to focus on the majority of the lecture today. So the states are equivalent to the observations, right? Whatever you observe is your state. There's nothing in the state that you don't know. So many board games, Go, Shallow, chess, etc. You observe it. Both people observe the full state, right? So that's fully observed. Okay, and partially observed are certainly some more difficult problems right in the middle, right? You know, all the main cases, the Darker Brain Challenge, the robot, it gets these sensor readings, it has to move, and so on. And that's really for my problem DPs, and again, I just want you to be aware that these things exist. I'm not going to tell you how to solve problem DPs today. Okay, so we covered actions, states, and observations. This is 3 parts of our 6 tuple. Okay, now we need to map between them, right? So we need to map from one state to the next. We need to map between state observations, and we need to say, well, how do we get rewarded for our behavior over time? Okay, and furthermore, we can say how we get rewarded at a time step. The question is then how to combine reward in multiple time steps. Okay, so how do I actually take this between states? So there are different properties of transition functions, right? I'm in the state, I take an action, I get the next state, right? The most common assumption is that your transition is stationary. It does not change over time. So transition matrix, if you have one, your transition probability to have it is always fixed no matter what point in time you're at. Okay? So now, if you think of, say, temperature, it's probably week or year dependent, so there are some non-stationarities here. How can I make temperature, the transition distribution from one state to the next, stationary? It's like, so today is 20, the next hour will be 21, right? But some time of the year, that would be a very different transition, right? In the winter, when we're back to 20, it might drop to 15 very quickly. It doesn't stay warm very long. Right? So in that case, based on the time that you're at, the point of the year that you're at, your transition will be different. But I claim that you can always make all transitions stationary. How do you do that? Anyone? Okay. Who thinks you cannot make transitions stationary? Okay, good, you were listening. Okay, so you agree it can be done, you're not sure how to do it. Well, okay, the issue is you can encode anything in your state that you want, right? If you start to encode the time of the year, or the day of the week in the state, right, then you can condition on that on your transition. Okay, and at that point, you have all the information in your state to predict the next state, that's in your time. So the thing is, making stationary, you just need to have the right information in your state to be able to predict the next state just from the current state. Okay? In NDPs, we're often obviously making the Markovian assumption is a Markovian decision process. This something means the next state is only dependent upon the previous state in action, right? So again, if it's not, just encode more information in your state, right? So you can almost always make a problem Markovian. Okay, so you can just call it state augmentation. So for example, what if your third remark column, right? It's actually the past 3 states that affect your next state. How do I turn a third remarkable problem into a first order remarkable problem, where just the previous state affects the next state?
So states becomes three last states?
Yeah, exactly. So in your state, store last state, second last state, third last state, right? So you can always do these simple modifications. Therefore, I want to submit that the Markovian assumption is not really a sufficient assumption in practice. Right, you have the power to model things. Okay, so often in standard planning, you have goal-oriented planning, where there's a goal you need to get to and you terminate. There could be some cost associated with that. So because NDPs work with rewards, we have to assign a greater reward for success than failure, but that's all. It does cost basically where you wouldn't achieve a goal if the cost to achieve it exceeds the reward that you get for success. But it's easy to code goal-oriented behavior NDPs in this way. But if you have one or no goals, this is the case you often see in NDPs. So imagine a mail delivery robot, right? It has to always go pick up mail from different places where the mail might come in. It has to deliver the mail to the recipients over time. Is there a goal when the mail robot terminates? No, right? It's continuing reward over time, day to day, year to year, if it works that long, right? So there are development problems that don't clearly have the time. They do have clearly defined objectives, but they don't have, which is like minimize wait time, minimize missed deliveries, but they don't have a clear goal where you just get there and you terminate. These are called process-oriented problems, and MVPs do model these well. Okay? So generally you have a reward for state in action, and you assign utilities each state in action. This covers action costs and everything else. You want to maximize the utility, but the question is, if I get reward 5 at this time step, reward 10 the next time step, how does it work rewards over time? Okay, so here's another interactive problems. Don't go on when people start to speak up. So we have 2 states, right? State 1 or state 2. You can take the action stay, which stays in the current state, and get to reward 2, if you're up here. And you can get, you can take stay down. So actually, if you're down here in state 2, you're forced to stay, right? No matter what you do, you're always staying in state 2, and you reward 0. If you ever start in state 1 and you transition at some point to state 2, you get rewarded 10. So what's the best action here? Or what's the best policy? Should I immediately transition? Should I go for 10 steps and stay and then transition?
Well, it depends on your horizon. But if it's infinite horizon, you should stay.
Okay, so you're assuming that I'm summing all the rewards of the horizon.
Yes.
Okay, good. Okay, so if your objective is sum all the rewards of the horizon, right? Then indeed you want to stay. You get infinite reward. Typically, you run into fundamental issues with MVPs if your reward can be infinite. So what's a way that I can reason over an infinite horizon, but not end up in infinite reward? So what's the standard assumption in MVPs? Discounting, yeah. So I might say, you know, I discount future rewards by 0.9. I have a discount factor. Okay. And then here you can see my discount factor is really high, so it is 0.999. Right? I'm going to want to stay. I'm going to get a lot of reward. What if my discount factor is like 0.1? Like I get it out in the current state, and then any future reward is 10% of the return. So if I have a very low, well, technically high discount, say 0.1 in the future, should I still stay?
Still go 0.
So I get 2, and then I get 0.1 of anything in the future.
Oh, anything in the future?
Yeah.
Okay.
Yeah. So, well, this is some of it, but it's recursively discounted. So, the point is, if you discount highly enough, if you discount the future enough, obviously you're just going to take the immediate reward and terminate. You know, and this is not so far from like, you know, different people have different discounts, right? If you're doing a master's or PhD, I would say that you have a high discount of 0.9, right? You can see 5 years out in your future, and you're willing to put up with the difficulties to get to the end of the degree. You know, if you stop at high school, maybe you were more likely to say, hey, okay, that's it, I'm gonna go make money. Okay, so discounting is an important issue in practice. Yeah, a different thing that you can do also is you can take an average of reward over time, which doesn't discount the future as heavily as the discounting approach. But the one thing is you have to ensure that the future reward stays finite. So if you're not discounting, you're not taking averages, you are taking the full cumulative sum, then you have to ensure that the problem goal-oriented, you will terminate. Okay, so an NDP is, anyone know what that's called, an NDP? Hector, you've written those papers on this. It's a Catholic insurance path. And read Hector papers for how to solve lots of Catholic insurance path problems. Okay, so then there's also the issue, so another way to keep the future rewards finite is to just assume your horizon is finite. Okay, and if you think about like chess or Go, a lot of problems, right? You're not acting forever, you are acting for a finite horizon. So, and in this case, your policy does depend on how many times you have to go. Like, the way you act in a certain game, you'll have 1 step to go is different than the way you might act if you have 10 steps to go. So if you have a finite horizon, then your policy will be will be horizon dependent. If it's infinite horizon, will prove that it's not. Your policy is stationary. It doesn't. The outer policy doesn't change over time. Okay, so you can take it. So in the infinite case, you can take, or in the finite case, you can use average or discount to return. So there we go. So these are all the ingredients. And I just, it's before I go in anywhere else, I just want to make sure you understand what the ingredients are. You want about a problem, you know what the actions are, what the states are, what are the observations. Transition function, how do you get from one state to the next, and actions you take? How do your observations relate to your states? Right? If I get a sensor reading that says I'm 3 meters to the wall, right? What if I believe in my state I'm actually 3 meters given a noisy sensor? Reward function, right? This is the thing you want to optimize over time. This tells you how to act. And finally, the reward's local for one state, and some optimization criteria tells you how you want to act over time. Okay? Then with all of this, you don't know whether the observation, the reward, the transition, etc., are known or unknown, right? And that's complicated things. So again, if I go back to the Dark Grand Challenge problem, do I know everything perfectly? Right, probably not. Okay. So then this gives you a few different cases, right? You have the model known case, right? And this again is what I call planning under uncertainty, right? You know the observation, transition, reward functions. You don't have to sample from the environment to learn them, right? You know them, so basically this is a plan in that model. That's planning under uncertainty. Okay. So just terminologically, planning is often going to be goal-oriented, right? So many years ago, we wanted to talk about maximizing expected rewards over time. They named that decision theoretic planning. I'm not sure if that term still holds, but historically, does that term still hold? Hector? Does decision theoretic planning still refer to the general reward case? I think it does. Sorry, I don't mean that. Which was fine. Okay, but if you don't have a model, right, it's more than one of these limits, the observation, transition, and the reward function, right? In this case, you have no observation sample of the real world, right? That's called reinforcement learning. Right, so here you have the interactive environment to obtain samples, and you really, the key thing in reinforcement learning is to really reduce sample complexity. So sampling is expensive. Sampling could say, hey, what happens if my robot goes to the edge of the stairs? Right? It could be really expensive. So the whole task in RL is how do you explore efficiently and safely? Okay. Now there's a case between model free and model known called model based, right? Which says rather than just try, which says rather than try to optimize a policy based on samples, I'm actually going to try to use my samples to build a model and then use model known techniques in planning, right? And this is typically more sample efficient, right? Because I have a model of the world, and I can, I think this is what humans do, right? We have a rough model of the world, we plan in that, then we act, and we see where we get. But it does require a lot more effort to build the model and maintain it. So all decision theoretic planning under uncertainty for me is just this tuple: states, actions, observations. Z is the observation function, T is the transition function, R is the reward, right? Okay, and you say whether all these are known in a priori or not known. There is actually a model, I'm not going to cover it, but Joe and I worked with Marcus Hutter for his PhD thesis, and Marcus takes this approach called ICAPS, where you don't even know what your state is, right? And I think it's like the most extreme case, but Marcus argues that is the general case of AI, which I would tend to agree with. Okay. So great, so, like Feynman said, write down the problem, think hard, write down the solution. So good, so as soon as you write down the problem, you're done, right? Yeah, just finding your, okay, well that's not so easy, right? The majority of the problem. So I would submit that modeling problems well is not easy. You want to model the right level of detail to capture the most important innovation for decision making. You don't want to capture irrelevant detail. So I think modeling is quite hard. Once you do that, you have to sort of efficiently find the solutions, and that's certainly harder computationally. Okay. But we do for all the other applications, the poker, the game playing, the government grand challenge. There are solutions or approaches in these cases. They're all quite different. It really depends on the problem that you model. Okay, so I'm going to cover model-based solutions to MDPs. Okay, so here's this very simple MDP. We have, this is the same one that I showed earlier, but this time in a finite state automaton view, or probabilistic state automaton view. We've got two states, S1 and S2. I can take an action staying with some probability. I stay in the states, and with some probability I move to state 2. And I have different rewards that I can get for taking different actions in different states. Okay. So now this is a fully observable problem, right? So back to the MDP case, no observations, no observation function. I always see what state I'm in. Okay, so my states here are state 1 and 2. My actions are state and change. My reward, okay, if I'm in state 1 and I take action stay, then I get reward 2. A transition here says, well, so what's the probability that I get to state 1 if I took action stay and I started state 1? Right? So we have in this diagram it's 0.9. Okay? Discount factor, well again, this is what you define, this is what you think is if you are discounting, and most of the talk I also you're discounting, right, you need to assume how important is the future versus the present. So I can rob a bank today and get arrested tomorrow, 10 years in jail, right? Okay, so how would you act optimally in MDP? In planning, you know that we just take a straight line deterministic plan from the start state to the goal state, okay? But it's quite different in MDPs, right? In this case, we have to define a policy that tells us when we're in a state how we get to an action. So why don't deterministic straight line plans work in MDPs? Why don't we have a policy that tells us how to act in any state we reach?
You might end up somewhere where you hadn't planned to be, but you don't know what to do.
Exactly. Your intentions are stochastic, right? So you should always condition your action on where you actually ended up. For example, this is an easy case, but there are other cases where, you certainly want to use all information available given that you don't know what the outcomes are going to be. So in any case, to be able to find a policy for optimality, it tells you simply what action to take in every state that you can be in. And again, if you're discounting it for a horizon, the policy doesn't change over time, it's stationary. Okay, so that's policy here. Again, depending on the discount factor. Discount factor, if you didn't discount, right? So 1.0, you get the full future return. Obviously, the output policy is if you're in state 1, you should take action stay. If you're in state 2, of course, you have no option. Okay? Again, if the discount factor is really low like this, then your output policy is in state 1 to change. Okay, so given any policy, it tells us how to act in any state. You'll see this a lot in the MDP literature, so make sure you understand it. It's straightforward. It says, what's the value, what's the long-term future value, the value function, of being in a state given I act under policy pi? Okay? So policy pi induces some stochastic distribution over future trajectory of states that I could be in. Right? And so basically, I can average or take an expectation over all those future trajectories of what's the sum from time equals 0 to infinity of the discounting of the reward that I get at time t in this trajectory, assuming that my initial state, that I start in some initial state S, right? So what's the long-term value of being in S and acting according to policy pi? That's your value. So this is nice because it allows us to find the optimal solution. There is a value function. This is a very good result. So you might say, are there in an optimal value function, right? The optimal value. Are there some policies that might do better in some states rather than others, right? Or are there two optimal policies that get different values? The answer is no. the optimal value function, right, is unique and strictly dominates all other value functions, right? So that's nice. There's no inherent trade-off in the future value of any state that you have to assume. There's a unique optimal policy, it dominates values for all possible states that you can be in. So all I have to do is find that beautiful, unique optimal policy. Okay? And nice thing about MDPs, single agent MDPs, is that there's always a optimal deterministic policy pi star, right? In the multi-agent case, if it's alternating term, right? I act, my opponent acts, is the optimal policy deterministic versus stochastic. Multi-agent, but or two-agent, but alternating term. Still deterministic. So when is the multi-agent case? When do I need to test the policy? Like, what's the property of rock, paper, scissors that makes me need stochastic policy in that case?
Does it matter whether you know or not if the other agent has the same policy as you?
No. I don't think that's. Okay, so just about like Nash equilibrium reasoning, right? What would I do even I know what my agent's going to do? But I'm a little more, what's the property of a multi-agent MDP that requires stochastic policy? Is that you act concurrently, right? Rock, paper, scissors is not like, give me rock, paper, scissors, right? And then you give me rock and I say, okay, paper, right? That'd be a dumb game, right? If you're acting concurrently, again, when you have a current action, if you have it at the same time, you don't know, that's when you need stochastic policies. But that's the only case when you need stochastic, otherwise deterministic. That's great because it actually, for any finite state, finite action MDP, there's a finite set of policies. One very dumb way to actually solve it is to enumerate all policies and all value functions. Fortunately, we can do much better. Okay, so now we can define the greedy policy, IB, which always takes the action each day to maximize expected value with respect to some given value function B, right? So what is the action that I would take if I'm in state S and I'm going to follow the greedy policy? Or sorry, I'm in state S, I'm going to get value B in the future. Well, let's look at how things decompose. I'm in its initial state, and I get some immediate reward, the state in action. And then I transition to a next state, and I say I'm going to get that value in the next state. But I transition to stochastic, so I want to actually average over all of the opposite states that I'm going to get into. What's their value? What's the probability of getting there? Right? So immediate, you always see this in the Bellman equation I'm going to cover. You always decompose MDPs into reason about the current state and then future reward. Okay? And obviously, whatever the action A is that maximizes this quantity, current and future reward, right? That's going to be my greedy policy with respect to the value function B. Right? Okay? And if you know you can act so as to obtain B in the future, then doing action A obviously guarantees that you at least get B of S in expectation. Okay? So in practice, often you don't know B exactly, but if B is a lower bound, right, again, you're going to guarantee at least that much value. If B is never bound, you know, if I walk out the door, I'm going to make $1 million, right? Good luck. So typically, we act in practice, we act according to lower bounds. They're safe. They guarantee a value. Okay. So this idea that the region of current future reward allows me to decompose regional MDPs sequentially over time by defining a t-1 stage to go value function. Because it says, what's the value I can get if I have t-1 actions left to take? Okay. So how would you act optimally with t decisions? Right? If I give you a t-1 stage value function, how would you act optimally with t decision, with one more decision? Well, again, you go back here, you take the action that optimizes the initial reward, and optimizes the future reward, the expected reward that's encapsulated in B. Okay, so you reason recursively of the current state and then knowing value from t-1 and in the future. Right? So to write this down, right? What's the value taking as a Q? Often Q for quality, maybe. I'm not always sure where Q came from. But your Q function says, what's the value that I'll get from acting in state S and taking action A if I have T decisions to go? And again, you can decompose that into a dynamic programming decomposition in terms of reasoning about the current state, right? And then the expected future what you're going to get if you know what BT minus 1 is. Okay. So then what's the best action? Okay, if you've got the Q values, right, telling you the value of every action, every state, what's the best value that you get? Obviously, just a max over the Q value. Does anyone recognize these two equations? Sorry?
Vaguely, but not really.
Okay. NDPs?
Is that the Bellman equation?
Yes, these are the Bellman equations, right? The one thing is, they're very intuitive, right? You know, I mean, I guess everything's obvious in retrospect, right? But this is just something, if you just think about it inductively, how do I act given some future value, right? You're just going to write this down. Okay. Now, if I start with some, so when I have 0 stages to act, right, I can only get an immediate reward, right? If it's not action dependent. And then so I know basically how to act with 0 time steps. I just take the action that occupies immediate reward. And this tells me now, for all t from 1 back to infinity, it tells me how to act optimally, right? Just inductively. And recursively decomposed. Okay. So if you do run this, right, you start with B0 as a reward, and you iterate this. It's called value iteration until t equals infinity, and you're discounting. B will actually converge to B star, which is the optimal value. Okay. Which means that, and what happens is basically you reach a fixed point where Vt and Vt minus 1 don't differ over any state. Okay? And this solution is known as, again, this solution, this is the development backup here. If you iterate the development backup, you do a value iteration, right? It's also known as dynamic programming. And I'll show you visually shortly why that makes, why it's called dynamic programming. Okay, so often in literature you see this thing called the development backup operator. It's an operator or function that applies to a function B and backs up the value function 1 time step. So there exists optimal value function B star and an optimal deterministic greedy policy pi star. It corresponds to taking the greedy action with respect to B star, right? These are both. So B star is unique. There could be multiple policies pi star, but they all achieve the same value. And an easy way to see that is take any MDP and just duplicate an action in it, right? If that action is in the optimal policy and it has a duplicate, it doesn't matter which one I take. Right? So it's easy to see that there might be multiple policies, but they're all going to have the same value. It's just a case basically of a duplicate action or equivalent. And again, the nice property of B star is a fixed point, right? You do the development backup of B star, you still get B star. This often suggests at least one solution approach. Okay, you can define the development error, basically, what's the disagreement between the development backup, right, in the state and the value of the current state, right? And when the development error, of course, goes to 0, right, then the value must be B star. Again, B star is a fixed point. Okay? And you can prove nicely that B is a contraction operator. So basically, if I look at the error of the backup value function, right, I reduce the error of the original value function by my discount factor. Okay? And this is basically a short proof, right? If you have this property, which is fairly easy to show, right? Then you can show that basically if I do k iterations of these backups, right, I'll get rid of the k reduction in error. If we're given the infinity, we put on the infinity, that's 0. So I took the error to 0. Okay. So does this suggest a solution? Again, this is the idea of value iteration, just to recap it. Because you know if you iterate enough, you will reach a fixed point. You start with V0 as a reward, and then you just iterate computing VT in terms of VT minus 1. Okay? Now, typically, it can take a long time to terminate, right? If you actually want the value to reach the actual fixed point, but basically you'll need to reach the fixed point within some numerical error. If you're discounting, you can determine what's the actual horizon that I need to act over, right? Before the future reward is irrelevant. So in practice, you only do a finite number of iterations, right? And then you converge within some epsilon tolerance of your solution. And you can bound the number of iterations based on discount factors. Okay. Good. So here's the graphical view to make things more obvious. So hopefully you guys are on the tree search. Let's talk about expect to max tree search. So here I'm in some state S. I take some action, A1 or A2. It's in the action. I have some distribution over next states, right? If I know the value at all the next states here, then the Q value is just the expectation, right? Multiply the value by the power of getting to them. I'm taking action A1, that's the Q value. So that's the expected part. And the max part of the expected max, and basically once I know the Q value, I max the actions A, well, what's the best action to take? Okay. So this is just the graphical view of your going back. I know BT, therefore I can compute BT plus 1. Okay. Now, why do we call it dynamic programming? If you think about it, what I could do is I could expand this tree out exponentially, right? It's a big tree, grows exponentially. And the computation there is exponential. But that would be a very naive way to do it, because basically, if I compute things recursively, BT and then BT plus 1, then I can cache my values, my BTs, and reuse them for the next computation. So I know B0, I can do an expected max from V1 of S1, right? And I can do expected max and sum, from S2, and cache those values. Okay? So then I've got V1. Now at V2, again, I can use the cache values of V1 to compute V2 of S1, V2 of S2. So suppose building this tree out, right, exponentially, which is obviously exponential on the horizon, I can do this instead. What's the complexity if I have S states and A actions and horizon A? What's the complexity of value iteration? Okay, so for any, so forget the horizon, just take horizon equals 1. I'm at V1. What's the complexity of the number of states and actions of this computation? Is it number of states times number of actions? That might be the first suggestion. Who's in a PhD program? Great. Okay. One of you guys answer this, right? You cannot get a PhD to answer this. Whatever. So is the complexity, right? I'm computing a value here. Is the complexity the number of states times the number of actions? Certainly for every state, I have to look at A actions. It's at least S times N. Is it more than that, or is it S times A? Not the answer. Okay. So it's S times A, so I'm only looking at most at one next state from A. Is that true? So if I take an action A, how many next states can I reach? You know, naively, if I don't know, if I don't need anything that's on T. I'm in one state, how many other states can I reach? S, okay. So you have S states compute the value for, you have A actions. For each of the A actions, there's S states that you can reach, and you have to compute a weighted sum over. So is it S times A? Sorry?
S times A times S.
Yeah, so it's S squared times A, right? It's actually funny, I think your viewers didn't realize that. They said it's S times A. No. It's quadratic the number of states, unless you assume, what you can often do in practice, is you only have k reachable states. If you know from any state you can only reach k of the states, it would be S times A times K, right? So k is a constant, and that's s times a. But in general, it's s squared a for a single horizon, and then for horizon h, it's h times s squared times a, right? Is that exponential? No, that's polynomial, right? And that's the beauty of value iteration, right? It's computing the same thing, and expand this tree out to some horizon h, that's exponential. Or I can cast my value and do recursively backwards, and it's polynomial, right? So absolutely beautiful result. I think dynamic programming initially came up in the context of solving the Dublin equation, but obviously now we use the term more generically for a lot of problems that can be reduced recursively in the current time, some current state, and some lesser reduced state or future state. Okay. Now, this is called synchronous value iteration, right? Because I always compute all of V0 before I compute V1, V2, V3. It turns out you don't have to do that for convergence. I can compute V1 of S1, and then I can compute V2 of S1 without computing V1. I can compute V2 of S1 based on V0. So this is called, so when you sort of randomly choose the states to update to the known backup for, that's called asynchronous, right? Kind of see it like this, right? You're only going to back up certain states. Okay? That still converges. And this actually leads to a very nice solution in MDPs called real-time dynamic programming. So what happens in MDPs is that a lot of your states are actually unreachable. At least from some initial state that you're in. So do you actually compute a value function over every possible state when you know you're never going to reach a lot of them? No. So what you can do instead is you can start from an initial state and just sample a trajectory forward, right? Sample the a trajectory forward out to here, and then I can basically, from the terminal state in my trajectory, I can just back up in reverse every state that I encounter along that trajectory. And basically, this conforms to asynchronous dynamic programming over the reachable states. By definition, because I'm only updating the states that I've actually reached through my sampling, I'm only updating reachable states. And because it's stochastic, I will update all states equally often. So very, very simple idea called real-time dynamic programming that basically just does a trajectory sample and then a back along that sample that still converges and much more efficiently practice. And again, if you want to read all about our VB algorithms, read about Hector's papers with Fly. Some really great papers there. But really effective solution in practice. Okay, so there are other ways there. So this is the value iteration approach. There are other ways to solve MDPs. And I can think of basically how to derive a policy directly. So I'm going to get to policy iteration for policy iteration. But first, the question is, given some policy pi, how would I derive the value function right over the policy pi? Okay. So there's two approaches that you can use. If you write down the equations, right? So when I have policy pi, I know I'm going to have a max of my action because I actually know what action I'm going to take in each state. That's given by pi of s. Okay. And you can still prove that there's a fixed point. That basically, if I act over an infinite horizon, some discounting, there is some b pi that will satisfy this recursive equation. And with a fixed, and then I'm maximizing over it, I fix the actions in policy. Okay. If you think about it, if I'm trying to solve for what b is, I know what r is, I know what t is. V is a free variable, one free variable for every state. I have one free variable for every state, and I have one linear equation. That's a constant, that's a free variable. One linear equation for every state. So I'm just solving a linear system to solve for v pi. And I know that you can do that via by actually solving a matrix inversion problem. So if your number of states isn't too large, so the matrix s squared, the s squared isn't too large, you can do this. But what happens when s is a billion? You have a billion states. Does anyone want to invert a billion-dimensional matrix? No, I don't know. Okay. So how would you solve, right, for v pi? You can solve for v pi in a billion-state MDP. How would you solve for it? You can't invert the matrix. It turns out that you can do successive approximation, right? It's kind of like value iteration, but without actually maximizing it over your action. right? You just iterate this. You start with some initialization, vt minus 1, and you compute vt of pi. Again, pi is fixed, but if you iterate this like known backup, again, with a fixed pi, right, it will eventually converge to the right fixed point. And that fixed point, v pi, is the value acting according to policy pi in state S. Okay? So there are nice ways to compute this without limitation conversion, which is nice. Good. So given any policy pi, I can compute the value acting according to the policy starting from state S. Now, how can I search for policies? There's an idea called policy iteration, which you've probably heard of. I start with some initial policy pi 0, any policy you want. And then I solve for what's the value of that policy. Okay. Now, I can even find a better policy by saying, well, okay, how do I act greedily? If I want to find a new policy, how do I act greedily with respect to this v pi? So this improves over the previous policy, where possible. Okay, I'll call that pi I plus 1. Now the beautiful result is basically if pi I plus 1 equals pi I, right? If the policy is greedy with respect to the value function derived from it, you know you've reached a fixed point, and you can terminate. And if the new policy doesn't match the previous one, then you know you haven't terminated, you haven't reached a fixed point, and you iterate. So basically, you can show that v pi is strictly increasing. And you know, again, modulo the issue of duplicate actions. So typically you should always try, if you have two actions equating the same value, you should always break ties deterministically, right? And that way, in the case of multiple policy being optimal, you always use the same optimal policy. But modulo that issue, this is a simple greedy hill climbing that's guaranteed to converge to the optimal. Okay. And you can actually, I won't ask you to do it, but based on the equations that I gave you previously, the fixed point, you can actually prove this. I did give it on a final exam a few years ago. It's actually only a few steps. Okay, so this is almost ending my coverage of the basic solution methods for MDPs. So I covered value iteration, and I just covered this policy iteration idea. Right? So value iteration, each iteration you do one step of policy evaluation. It can be seen as one step of policy evaluation for the current data policy. And you're always using the previous policy's value to say what's my future value. Policy iteration, you do a full evaluation of v pi for the current policy pi. So not just like a one-step evaluation, but an infinite horizon evaluation. Okay? And then you do a greedy policy update. And you can stare at this long enough and say, well, there's probably some midpoint between. That's called modified policy iteration. Where basically, you kind of do some number of iterations of policy evaluation, but not to convergence, and then you update the policy, and so on. This is basically interpolating between value policy iteration is still convergence. So this is a very nice fixed-point operation of MDPs that always guarantee convergence, no matter which approach you take. In practice, they typically see value iteration and policy iteration. I just want to let you know there are other methods. Okay. I'm going to switch directions. So this is just a few more slides. I'm going to switch directions, and then the coffee will come, we take a break, and then Joe will tell you how to solve Go and other cool problems. So solve Go and Atari, right? But if you solve these problems, you can probably do some other cool things with them. Okay, so now clear your mind of fixed point equations. We're going to talk about modeling just MDPs here, but Riddle is also a language for modeling POMDPs. So how do you model a really large problem? Okay, I'll skip the background. Probably not too problem for you guys. Let me go straight to this. Okay. So imagine that we have this problem that's known as wildfire. It was actually initially introduced in the ecology literature. You have a grid of cells, right? You have a forest. The cells have trees in them, or they have target infrastructure, houses, buildings, etc. Things that you don't want to burn in a forest fire. So every cell can be green, you know, it's just a happy tree. Thank you, Bob Ross. or it's a target you don't want to burn, or the cells can be on fire, that's red here. They can be burned out, which is black. Or you can build a fire line. You can remove the flammable materials, the underbrush and so on from regions or dig fire ditches, etc. So you can turn cells brown, right, to sort of build a fire line by making those cells harder to burn. Okay. But once the fire is burning, it tends to spread stochastically to neighboring cells. Okay. So the wildfire problem is how do I, stochastic problem, how do I optimally, you go have some finite resources with your fire brigades. How do I determine which cells to remove the underbrush and dig fire lines for, right? Given the limited resources, given the stochastic outcome of the fire. Very difficult problem. But I want to think about how we're going to model this problem, right? And how we're going to model it compactly. How many states? So let's say we have 4 states for a cell. Just for simplicity, we'll even the target states never change. We'll still say a state itself can be a target. It can be green, right? It's a happy tree cell. It can be red, burning, brown. It's flammable materials have removed, or it's black. So let's look at the states of green, brown, red, and black. 4 different states of a cell. Okay. Now here I have, I think, 10, it's 9 by 4, I have 36 cells. Okay. So forgetting the T's, how many total states do I have here? Every cell can be in 4 states. I have 36 cells. How many states do I have here? 4 to the 36 power. Yes? Yeah. So extremely, it looks like a very simple problem, right? 4 to the 36 number of states. Who wants to write down by hand the transition model for that problem? Okay. Start now, and I'll come back in a week, see where you are, right? So, okay, this problem should not be that hard to model. But what we can do is we can't write it down naively with a transition matrix. And the reward vector might not be so hard to write down. Actually, it would be, because think, the reward vector has to specify a different value for every 4 to the 36 states. Like, I don't know what that number is. 2 to the 2, it's large. So, it's well over a trillion states, much larger than that thing. So let's just say we have a trillion states, right? The reward vector is a reward value for each state. Okay, you're not going to write that down. The transition matrix is a trillion by trillion matrix of transition probabilities. Okay, can't write that down either. So does this mean that this seemingly simple trivial problem cannot be written down? No, it can be, right? And of course, you have exactly the same problem in PDDL and so on, right? You have these very complex state configurations of PDDL models and very compactly. It turns out NDP, since it deals with stochasticity, and lots of independently interacting events, need a completely different model. Okay. So I don't know, who's heard of dynamic Bayesian networks? Okay, so you might recognize this part of the middle, right? If I have a variable, right, so each variable here, xi, is going to be cell I, it takes on 4 states, right? And I can specify what's the probability of the next state burning or being burnt out, etc., given the probability of the previous states and the actions. So I can write the problem in a factorized form, where I'm representing individual cell properties and the probabilities of those cells. But one thing to notice is that all the cells act the same, right? The way fire is present in one cell is the same as present in other cells. So what I'm going to do is I'm going to specify things like these dynamic Bayesian networks, but I'm going to specify them very compactly. Okay, and that's the whole point of this brittle language. So let me show you how to model this problem compactly. Okay. So for every cell I have position X and position Y. Okay. And I'll have 2 booleans, one for the cell burning or not, and one boolean for the cell X, Y out of the field or not. This is where the 4 states come from. Okay. And you say, well, how is the state burning, right? How can I know the probability of a state burning in the next state, given properties of my actions in the previous state? I'm going to write this down as what's called a stochastic program. It's a program that values stochastically. This is uncertain. So every next state variable is going to be the conditional probability is defined implicitly via this stochastic program. Okay. So is cell X, Y burning next state? Well, if you take the action and put out the fire in that state, then of course it's not burning, it's false. Deterministically, burning part is false. Okay. However, if the cell is not out of fuel, so you didn't take an action, it's not out of fuel, and it's not burning, right? Then whether it's burning depends on the probability of the burning spread from neighbors. Okay? And there's assumption the ecological literature, the more neighbors that are burning, the more likely you are to burn. Right? In fact, there's a sigmoidal function to model that. So here what I can do, this is the thing that you do in the different language, you can sum over all neighboring cells, x2 and y2, okay? You get a value of 1 if the neighbor relationship is true, and you get a value of 1 if it's burning. So this summation basically sums, repeats the sum of all neighbors who are also burning. Okay? And I know because in a grid that's between 0 and 8. Okay? So I take that number between 0 and 8, and I pop through a sigmoidal function, whatever one calls exponential, and that gives the probability, right, that I'm actually going to be burning. But it's a stochastic, right? Nature is stochastic. So it's a probability of burning 0.9, and I sample from Bernoulli, a coin flip, right, from that distribution. Okay? But again, it's a very compact way to say the more neighbors are burning, the more likely I'm to burn, and the relationship is nonlinear, right? You can do that in one very simple programming line. So writing Griddle is kind of like running a simulator, right? And that was actually my initial motivation for Griddle. It's very easy for people to write down simulators domains. It's a little bit harder to write transition models directly. Okay? So I didn't put out the fire, and it didn't spread from neighboring cells because it wasn't burning, right? Then basically, the previous burning state persists, whatever it was, be it true or false. Okay. Reward, likewise, I obviously want to think about, the ideal case is that I put out the fire in all cells, but if I have 10 cells burning in one state and I have 20 cells burning in the other state, well, I certainly prefer 10 to 20. So I want to minimize some of say, target cells that are burning and some non-target cells that are burning. And also, there's also calls for taking actions, right? The fire brigades are not free. So there's also an action cost for what it takes them to put out a burning fire and what it takes them to cut out the underbrush or to cut a fire line. Right? So all these costs that I'm reasoning about, the cost of the fire brigade, the cost of non-target burning, the cost of target burning, and that's my reward function. It's additive, but again, it's very easy to specify over all cells. It's just this sum operator. Okay. So here's this, over 1 trillion by 1 trillion matrix and 1 trillion state reward function, and I've written it down, in maybe 10 to 12 lines of program code, right? And you guys can understand this model this. So, if you go to modeling MDP, I submit to you that you're going to want a compact language, and I'm going to highly recommend that you do look at Griddle. So compared to, so this sort of probabilistic PDO, the probabilistic PDL is nice in that it does look just like PDL with some probabilities. What you don't get, though, is the fact that every cell can independently burn, right? So PDL kind of requires correlated action effects. There's one contract that does break that, but in general, we have lots of independent stochastic events. It's a lot easier to model Griddle. In fact, there are problems that you can model Griddle you cannot model probabilistic PDL. What this was easier was actually more expressive. Okay, so most software used in practice don't operate on the reward functions and matrices. They operate on the dynamic Bayesian network view, right? That's called a factored representation, called a factored MDP part of it. And then our riddle is, I've written the translator, takes a program, a stochastic program, is automatically which is this probability program, easy to write and debug and simulate, right? Now our translator translates that stochastic program into a very large demonstration network. Now that's done for you, so you don't have to do it, but then you can take that demonstration network and you can feed that to an existing vector NTP solver. Okay. I did run a competition in 2011 and 2014. Right, this is how it worked. We specified the domains like wildfire. I gave people the debian translations and they found them. And so if you just look up my web page or Riddle, you'll find it online. I won't go through more than that. But just as we get to the break, so I run two competitions, and I just want to point out, this is a good segue into Joel's part of the tutorial. So prior to, purposely PDDL allowed you to specify a certain restricted set of MDPs that facilitated determinization approaches. Determinize the domain, solve that domain, and use that as your policy. Okay. And certainly for domains that can be modeled as probably PDDL, determinization was a great idea. When you have tons of stochastically interacting events, like a wildfire, every cell can burn independently based on its property, based on its neighboring cells, right? It turned out that a different class of solutions was more effective in these heavily stochastic problems, heavily concurrent stochastic problems, right? It turned out that the methods that worked best here in both 2011 and 2014 in the competition with Riddle were actually multicolor tree search domains, right? Based on an original algorithm called UCT. Okay, and that system was by Thomas Keller. Thomas is having twins very soon, so you have to catch him next year. But you can read about this work in different ICAPS papers. But the key thing is that state-of-the-art methods for solving very large MDPs that are stochastic would be multicolor tree search. Okay. And that is going to segue into what Joel is going to cover, right? That not only solves Go games, it'll solve Atari games, and hopefully lots of other problems. Okay, so I'm going to end there, and we'll have a coffee break, and then Joe will pick up with these winning approaches to competitions. Okay, thank you.
Where?